We will discuss the basic principles of switch mode power conversion as applied to DC-DC converters in a series of several videos. So the main topics to be covered are the bipositional switch, the concepts of pulse width modulation or PWM, cycle by cycle averaging, and this concept of DC steady state as applied to switch mode power converters. Then we will study the three important principles which are valid in steady state, namely the volt second balance for inductors, the current second balance for capacitors, and the power balance principle. In this video, we will begin with the bipositional switch. In a previous introductory video where we actually compared the linear electronics approach versus the switch mode power electronics approach in solving certain power supply problems, we introduced this very basic step down converter. So for example, the application that we considered was a power supply problem where we have a 12 volts input and we wanted a 5 volts output, and in the linear electronics approach the transistor actually dropped the different 7 volts and while carrying the full load current, and it incurred very high power loss. Whereas in the switch mode approach we use high frequency switching to get a lossless power conversion from 12 volts to 5 volts. This bipositional switch shown right here, this is the device that helps us do this lossless power conversion. So it helps us to connect this pole, called that as pole A, to one of two possible positions, call them as position 1 and position 2. So the position 1 is connected to the positive end of the DC voltage source, and position 2 is connected to the negative end or the ground of the DC source. So by appropriately controlling the time for which A is connected to position 1 relative to the time for which A is connected to position 2, we can actually control the average of the voltage that appears at the output of this bipositional switch. So that waveform is shown here. So this V sub A is the voltage at the output of this bipositional switch, and in this example we will control it such that the average VA average is 5 volts as we need for the output voltage. So in this specific application we would just filter out the high frequency component of this waveform so that at the load or at the output we only have this DC 5 volts. Okay. But in general this is the basic principle of many of the switch mode DC-DC power converters, where we actually control the output, in an average sense, the output of the this bipositional switch in order to realize many different objectives. In this example, the objective was to regulate the output voltage, and we do this switching at very high frequencies in order to reduce the size and also the cost of the filter components, the L and C, and also to get a higher control bandwidth and therefore a better control performance. The bipositional switch is not unique to the step-down converter. In fact, it is seen in every power converters. So for example, this figure shows a boost DC-DC converter where the output voltage is higher than the input voltage, and here is the bipositional switch in a boost converter. Similarly, the second figure is a buck boost DC-DC converter, and once again you see this power pole here which connects this pole A to either the positive end of the input voltage or to the negative end of the output voltage. Similarly, if you look at slightly more complex converters like a full-fledged 4-quadrant DC motor drive, where we can adjust the speed, the direction of rotation, and the torque, both positive and negative torque, regenerative braking. So that DC motor drive can be realized using two bipositional switches as shown here. This is switch 1, this is switch 2. And even in a DC to AC or AC to DC applications, just by having two bipositional switch, we can interface a DC source to an AC grid, or the power flow can be from the AC grid to the DC source. The main point is this bipositional switch is seen in almost all power converters, and in fact we can even call this bipositional switch as the main building block of a majority of the power converters. So this is the SPDT, or a single pole double throw implementation of the bipositional switch. Now there are mechanical SPDTs, single pole double throw switches, but there is no single electronic switch which can do the function of a single pole double throw switch. So we implement the bipositional switch, or this SPDT, by having two SPST switches, electronic single pole single throw switches. So basically this is nothing but a simple on off switch, but we need two of them. So for example, if this pole A needs to be connected to position 1, so this would be position 1, which is connected to the positive end of a DC source. So if you want pole A to be connected to position 1, then we will have the top switch on, and under the same condition we need to have the bottom switch off. Okay? And then when we want to connect the pole A to position 2 is here, this is 1, then we would turn off the top switch and turn on the bottom switch. So this way, by having two simple on-off switches, or two SPSTs, we can realize the function of a single SPDT. Okay, and now in all practical converters, it is a requirement that the two ends of this bipositional switch, these two ends or these two positions, so across the two positions we should always have a voltage, not necessarily a DC voltage source, but a voltage that is not pulsating. It's almost a constant DC voltage. And similarly, the this pole current needs to be a non-pulsating, a non-switching, but a continuous DC current for DC-DC converters. Okay. So those two conditions are represented by having this large capacitor across the two positions and this inductor in series with the pole, to show that the pole current is a non-pulsating current. As we analyze various converters, we'll see that in all power converters these two conditions are always met. Now we know that these two switches are switched at high frequencies, and they are used to control mainly the average of the pole output voltage. So therefore we need a switching signal for these two switches. Okay? And that is derived from a control voltage which comes from the output of some closed loop controller, and a pulse width modulator which converts this control voltage to appropriate switching pulses suitable for driving the two switches of the bipositional switch. So in later videos we'll learn about this PWM block, and much later we'll also look at how to design the controllers. So the output of the PWM block is the switching signal, and we call that as Q sub A. Q stands for the switching signal, and the suffix A is that corresponds to this pole A. Okay. So if there are multiple poles in a converter, then we will have QA, QB, and so on. So the output of the PWM block, this Q sub A, is given directly to the top switch, and the same signal is inverted by this NOT gate, and the inverted signal is applied to the bottom switch. So this way we ensure that the two switches are complementary, meaning they never switch on simultaneously or switch off simultaneously, except we will see later that there is a small dead time applied. But as of now, these two switches are switched complementarily. When one is on, the other one is off, and vice versa. Okay, then we come to the actual electronic implementation of the bipositional switch. So here is the electronic implementation of a complete bipositional switch. So we know that we implement the bipositional switch by having two simple on-off switches, or two SPSTs, as shown here on the figure on the left, and each of these SPSTs is realized by, in general, a single controlled switch, this Q1, and a diode across it. Similarly, the bottom SPST is also implemented by a single controlled switch and a diode across it. So this gives you, as I mentioned, the complete implementation. Later slides we'll see that there are some simplifications that can be done depending on the specific application. And these controllable switches, they are controlled by this switching signal Q, or Q sub A for pole A. So then I will also introduce the convention that we will be using throughout. So when Q sub A equals 1, that means by our convention, the top switch here, or Q1 in this electronic implementation, is on, and simultaneously at that time the bottom switch Q2 has to be off. Okay? So because the pole A is connected to the positive end of V sub D, the output of the bipositional switch defined as V sub A here with respect to the ground, that is equal to positive V sub D. And when QA equals 0, so this Q, which is a switching signal, can only take two values, either 1 or 0. If it is 1, the top switch is on. If QA equals 0, it means by our convention the top switch Q1 is turned off and the bottom switch Q2 is turned on. And when Q2 is on, it is easy to see that V sub A is actually shorted, so V sub A equals 0. Now when we have the bipositional switch implemented using this full set of two controllable switches and two diodes as shown here, and these two switches made of either MOSFETs or IGBTs, two of the most popular switching devices in DC-DC converters, and we'll be learning much more about these devices in detail in later videos. So when we have this full set of all four switches, then the pole current I sub A can be both positive and negative. It can be bidirectional. So the diodes obviously conduct in only one direction as indicated by the direction of the arrow, and similarly the IGBTs can also conduct current only in the direction shown by this arrow. But between the IGBT and the diode, each of these two switches, the top and the bottom switch, can conduct either positive current or negative current. So therefore this is a completely bidirectional current supporting device, whereas the output voltage V sub A can only be unipolar. So in the previous slide we saw that VA equals the input DC voltage VD when QA is 1, and it is equal to 0 when QA equals 0. Therefore both the instantaneous VA as well as the average VA cannot be negative. It is only unipolar. Okay? But with the current being bidirectional, we can support bidirectional power flow. Okay? So it means that the power flow can be in either this direction P, or it can be in the opposite direction. All we need is the appropriate load or the source on either side, and then by suitable control of this switching signal Q, we can control the power flow in either direction. Okay, next let's go ahead and determine exactly which of these four devices are conducting under different operating conditions. Okay, so essentially we are going to fill this table. So consider the case when the pole current IA is positive. IA is greater than 0 in this row. Okay. So with that, when Q equals 1, which means one of the top two devices have to conduct, and since IA is in this direction, the device that has the correct that can actually conduct this current is Q1, because the diode cannot support a current in this direction. Okay. So therefore the conducting device for IA greater than 0 and Q equals 1 is Q1. Similarly with IA still positive, so we need a current in this direction. Okay, but so I should not have deleted this. This is Q1. So when QA is 0, which means one of these two devices have to conduct, and only D2 has the correct current direction in this direction. So therefore the conducting device when Q is 0 to support a positive current IA is D2. Okay. Similarly, if you consider the case where IA is negative, meaning the current is actually flowing in this direction, okay, then when Q is 1, only D1 can support a current in this direction, and the conducting device for IA negative and QA equals 1 is D1. Okay. And the last case is when QA equals 0 and the current is IA pole current is still negative. So that then we can see that the current direction is like this into Q2. So therefore this is Q2. Okay. Now one of the reasons why we went through this exercise is to establish that if the pole current is guaranteed to be always less than or equal to 0, okay, then we are only operating along this row, and all we need is Q1 and D2. We do not require Q2 or D1 to be conducting under any of the switch, for any value of Q. Okay. So therefore, if you're guaranteed that IA is always positive, then we can just replace the bipositional switch by just one controllable switch and one diode, and they would be Q1 and D2. Okay, and that is indicated here, and this is the complete implementation of the bipositional switch, and this implementation can support bidirectional pole current. So whereas for unidirectional IA, which also results in unidirectional power flow because the voltage is always unipolar, and if the current is unidirectional, then the power flow is also unidirectional. Okay. For those applications, then all we need is this one switch and one diode. Okay. So we'll see that at least in our initial discussions on several basic DC-DC converters, we'll be using this implementation for the bipositional switch, because there are numerous applications, especially in DC-DC converters, where we are guaranteed that IA is always positive, and that is because the power flow is from a set source side to a set load side, and there is no reason for the power flow to reverse. Okay. So for example, in most power supplies for electronic equipment, the power flow is always from a source end to the, for example, the microprocessor power microprocessor loads. Now, in either of the two implementations, whether for bidirectional or unidirectional IA, the controllable switch, they are controlled by the gate signal. Okay. So they turn on and turn off of the IGBTs. The two IGBTs here are the single IGBT in the other implementation. They turn on and turn off or by applying or removing the gate drive signal. Whereas the operation of the diodes, again in both implementation, that is controlled by what happens in the circuit. Okay, so whether the circuit applies a forward bias or a reverse bias for the diode, and that determines whether the diode is off or if it is conducting. The MOSFETs or the IGBTs, they are not signal level devices. They are high voltage, high current devices. And presently the MOSFET and the IGBTs are the most popular device, mainly because of their high frequency characteristics, low switching transition times, and the ease at which they can be driven on and off. Similarly, the diodes are also not signal level diodes. Those are power diodes, and because of the high frequency operation in most power converters, we have to use what are known as ultra fast diodes. Now a question may arise on why we use a fully controllable switch for the top switch and an uncontrolled switch, the diode, for the bottom switch implementation. The reason is, recall that we need these two switches, the top and the bottom, to be complementary, meaning when one is on, the other needs to be off, and vice versa. So when we have this controllable switch, when this is turned on, when the IGBT is on, it automatically applies a reverse bias. So the diode is reverse biased by a large voltage of magnitude V sub D. So that will turn off the diode. Okay. And when we turn off the controllable switch by removing the gate drive, the current, the energy stored in the inductor, or the inductor current, would force the diode to conduct because there is no other path here. So this current I sub A has to be continuous because it is an inductor current, and therefore the inductor would force the diode by forward biasing it. So it automatically turns on without applying any gate drive. In general, diodes are less expensive compared to a fully controllable switch, and there is also no requirement or no further complexity of gate drive and so on. So if we can do with a diode, we prefer to have a diode instead of a fully controllable switch in most cases. Now, let me say that for a large part of our analysis in several upcoming videos, we will be assuming ideal devices, ideal switches and ideal diodes for the sake of simplicity of analysis. But I think it is also important, even at this stage, to be at least aware of the things that we are neglecting in assuming ideal switches. So the non-idealities present in real switches that are commercially available, they are listed here. The first one is switching losses. So when we give the gate drive to turn on or turn off, there is a finite non-zero time during which the voltages or the currents, they are rising and falling, and during those transition there is an overlap of very large currents and voltages, and that results in very high instantaneous switching loss. Okay? And higher the frequency, higher is the average switching loss. Okay? So that is one main non-ideality. Second one is the conduction losses. So when a device is conducting, ideally there is no voltage drop across it, but practical devices will have some voltage drop. In a MOSFET, for example, the on state can be modeled as simply a resistance. So the R times the conduction current is the voltage drop. So this voltage drop results in conduction losses depending on the current magnitude. Gate drive losses, MOSFETs and IGBTs are preferred devices because they consume little gate drive losses. But if we talk about really high frequencies, for example in the order of megahertz, then the gate drive losses are no longer negligible. They can be a significant part of your loss budget. And finally, there are several parasitic elements. The chief among them are the junction capacitance of the devices, the stray inductance and resistance in the wire leads, and these parasitic elements result in voltage spikes or current spikes. And finally, when we design when we select the switches and the diodes, we have to ensure that the permissible limits on the voltage rating, current rating, and the power rating, and also the junction temperature rating, they are not exceeded even under transient conditions.